All right. Welcome in, everybody. I think we're all set here and good to go. Good. Everyone's getting their name there in chat, so I can have a record of that. Great. Okay, good. I think I've got everything set up and prepared and ready to go. So a couple of things I want to talk about here at the beginning of things. So a couple things here. You have, I think, due tomorrow, you have this Discord preferences. A bunch of you have already left information in there, and I've actually gone in and read some of them. This is very helpful because I'm about to set one up for my future classes. So any kind of helpful advice you can throw. I mean, I've made Discords before for different types of things, but it's helpful to get that student perspective about like what do you like? If you were going to a Discord for a class, what would you want to see in there? Do you want to see the rooms where you can have I forget what they're called, but where you can have voice chat? Is that super important to you? Or like, what is the thing? Do you want what do they call it in Discord? I forget what they call it, like Flare. Do you want Flare in there so that people can have like, you can specify that you're in this class or you're, whatever. Any kind of ideas like that you find helpful, either that you've had in other class Discords or just that if you're someone who's familiar with Discord or you've used it, whatever, like, or you've used it this semester, just any kind of advice you can give me so that the first time I make a Discord for my class, it can kind of be as good as I can make it rather than having to learn over a few semesters what works and what doesn't. So because the Discords I've made in the past were for different purposes, not necessarily going to be set up the same way as for a class, right? So any kind of advice, it's an easy 10 points. Just go in there, give me your feelings about what you want to see in a Discord for a math class, and then I'll try to get that implemented for my future students. But I appreciate your help with that. So there's that. That's obviously important. That's due tomorrow. Easy 10 points. Make sure you get that. The practice exam was posted yesterday. Should be available to students, so you can go in there and here's your practice exam, and you can print that off and you guys can help each other out and work together, work by yourself, go to the tutoring center, whatever works for you. Do that so that you know how to do these kind of problems. Again, the test is not identical to the practice test. It's a little bit of difference, especially since, as I'll show you in a minute, they're on different platforms, right? The practice test is a written test that I've written out for you. I mean, not by hand, but it's like you can print it off as a PDF. The actual test that you're going to be taking it's a test version, but it's like in my math lab. So it's kind of like the homework you've been doing. It'll look like those problems in there. So the problems are a little bit different, but the practice test is just meant to give you an idea of these are the kinds of things that I ask on a regular basis. It doesn't mean the problems will be, well, he asked this type of equation here, so that's the only, like especially with like logarithms and exponentials, people do that where they're like, oh, well, remember there's like 5 or 6 different types of log and exponential equations. And some people go, oh, well, you didn't have this one on the practice test, right? That's not the point of the practice test, is to do every possible problem. I mean, otherwise there'd be hundreds of problems, right? So it's just to give you a general sense of where you're weak and where you're strong, and you have a few more days in those areas where you're weak to get strong. Okay, so it's kind of a starting point for your studying. Go in there, take the practice test by yourself. Right, I highly recommend you start off by taking it by yourself. Now, I highly encourage you later to get together with other people, either in the Discord chat rooms or on Zoom or in person, whatever it is you all want to do. Sometimes it's really nice with 6 people, 4 people, 6 people, whatever. Get together in one physical location and you work on that stuff together. That's kind of hard to reproduce even on Discord or something, but Discord is still tremendously helpful over like being totally by yourself and isolated and trying to study for this kind of stuff. So practice test. But again, use it to practice yourself so that you know where you're weak and strong. Once you know where you're weak and strong, then get together with other people and work the rest of it out. Talk it out. You're all going to learn from each other. And even if you feel like you know this stuff, the act of helping other people with it, essentially tutoring them in it, will strengthen your understanding of it as well. So, because when you explain something to someone, you kind of have to organize it, and sometimes like sometimes when you're explaining something to someone, you go, oh, I actually understand it even better now that I just explained it to you. So it can be very helpful. There's a good question here. Are you able to show us where the exam is located in Pearson, or does it pop up that day? I don't actually know what it looks like because it gives me the teacher view, and I don't think for this part there's a student view. But so I have the, let's see if I can pull it up actually. If we go in there, and I go to, be careful what I click so I don't expose anybody's grades or anything. Let's see, where are we? I did this the long way. Instead of just going straight to Assignment Manager, I went the long way in here. But so you see I've got it set up down here at the bottom, Exam 2. And it's all set to go live on the 28th at 11:45 a.m. So I have it set to go live about 15 minutes early. So you're welcome to start it at 11:45 if you like. The reason I set it for 11:45, even though technically we don't meet till 12, is that way, if there is some kind of an issue, that gives me 15 minutes to try to take care of it before we get to noon, right? So I think it's all set and ready to go. It should be fine. But in case there's some kind of weird issue, that'll give me a bit of a heads up because people will say, oh, the test is not available. So I don't know what it looks like from the student perspective on your end when it says like, oh, this is coming. But you can see it's supposed to go live at 11:45 on the 28th, and then it's going to close at 2 p.m. on the 28th. So it will close whether you're ready for it to close or not. So just sort of be ready for that. But it will happen here inside of the My Math Lab. I don't know if you go to that main home screen, if it will show you as like upcoming assignments or something. Because my page just looks different, so it's kind of hard to say. But it should be available to you. It should be obvious on Thursday when you come in that it's there. And speaking of which, so the way this works is I want to see your work. So it's just going to be like a homework where you're answering the questions. So you'll get a grade for that, but the grade is not like official until you've turned in your work, okay? Basically showing me that you did the problems, that you know how to go through them. So it'll be graded just like a normal test. So if you close the test and you're like, I think I got a 90, not necessarily. Like I still have to see just like on a regular paper and pencil test in class, if you were to just write 45 on a problem and no work was shown, you would get a 0 or maybe 3 points out of 10 or something like that. But you would miss many of the points because you didn't show your work. So I need to see that. So you can see here I have it set up. Please read instructions carefully to avoid being penalized. So on Thursday at noon, take exam 2 on My Math Lab. And then what you're going to do is you're going to come in here. This is really important. So everyone, if you don't understand this, make sure you ask because I don't want people to get low grades because they didn't understand what I was saying. Then what you're going to do is you're going to come in and you're going to upload your assignment here, like your work that you did. So when you're writing it out, don't just have like crazy work where you're just writing everything scratch work. Like make sure I can read it. So if I go to your work, I can say, okay, where did she work on problem number 3? Oh, here's problem number 3. Oh, and I can follow along what she did. And I can see that she actually did the work. What about this other guy on problem number 7? Oh, here's his problem number 7. I can see his work. I can understand it. Yes, he did the work. So it's just like the requirement in every, basically every math class you take that you have to show your work. It's the same thing here. You're just going to upload it either by scanning it and submitting it as a PDF. You can submit pictures from your phone, whatever works for you. But just make sure you get those in to me. In fact, I'll give you a little more time to get these up, but you have to do it relatively quickly, right? Where's the close time? Let's make it do, let's go 2:30. So you don't have that much time after the test closes to submit that stuff. But like I say, you can submit an image from your phone of your work, right? Just submit each picture of each page. You can submit it as a PDF if you scan it, whatever works. But I have to, I have to have some kind of a way that I can justify, if someone was to question the class, I can say, no, I'm holding them accountable. I'm making sure they're actually doing the work. See, here's the work that they turned in that goes along with the problems that they did. Because that's that's one of the major issues we've seen since going online is, and I'm not saying anyone in this class, but many students take online math classes specifically so they can try to, cheat on tests and stuff like that. Many students don't do that, but we're definitely seeing students who are trying to take advantage of that. So I have to be able to say, no, look, they're not just filling a number in a box. They're actually like doing the work here. Okay, so that's really important. Make sure you do that. Otherwise, if I don't get your work submitted in here, you're going to get a huge penalty on the test, like really big, like, massive penalty. So make sure that you show me your work so that I can just basically I can defend, no, this student actually, she didn't cheat or he didn't cheat or whatever. They actually did what they're supposed to do. So hopefully that's clear to everyone that you have to do that. I'll remind everyone on Thursday, but just make sure you're prepared to do that, whether that's having a phone you can use to take pictures or a printer you can scan with or whatever it is that you want to do. Let's see, where was I? I think there was more I wanted to say. So there's those two things. So there's the Discord preferences, practice exam, and the exam. Oh, so I guess that's it. And then, I know what the other thing was. I have extended a few homework chapters. The reason being, generally what I do with classes is when they end, like when students take the final exam, at the end of the exam, I literally sit down and start calculating final grades for that class, and then I submit them. Like sometimes within hours of the final exam, I'm already submitting grades. I won't be able to do that this time around because literally when the grade ends, I have to go get in the car and drive away for the weekend. And I won't be back until late Sunday. So what's going to happen is Monday, probably Monday morning, but sometime Monday, I'm going to sit down and I'm going to calculate grades for the course and I'm going to submit them on Monday. That probably means that you'll see them Tuesday, but you might see them late Monday. Just depends. Sometimes the servers run at a weird time and then the grade, they call it rollover. The grades roll over and become finalized and I can't change them anymore without like a bunch of paperwork. They roll over and then at that point they're available to students. A lot of times that server runs in the middle of the night. So at midnight or something, that server will run and it'll do all its tasks and finalize grades. And then the next day, students can see them. But sometimes it runs in the afternoon or something. And then so you get it a little bit earlier. But anyways, you should be able to see your grades Tuesday. Because of that, I've decided to extend some homework because the class doesn't technically end until June 30th, which is like Saturday. It's kind of weird. Obviously, we can't have like tests or anything on that day. But since I'm not going to be around to grade, I'm leaving it open that you can keep, if you want, you can keep working on those homework assignments and get more points if you think it's going to help you pass or you think it's going to help you get your A or whatever it is that you're trying to do in the course, whatever your goal is, working on the homework may benefit you. Now, what I will say is you want to be careful with that because homework is really where you learn the material. Right? You can come and watch me talk about stuff, but until you're doing it, like people don't understand, like you have to do things in order to learn, right? I'm sure most of you do understand this already, but many students don't. You have to do stuff in order to learn it. You can't just passively watch someone and go, oh, that would be, okay, I totally get that now. Like you might have a strong understanding of what's going on, but until you're actually doing the thing, it's just not the same, right? Like you can go home and watch all these Python videos, but until you're actually coding in Python, you don't really know what you're doing. So that being said, that means that you should try to do as much of the homework as you can before the exam, right? It doesn't make sense to take the exam and then go do the homework because then you're going to learn it after the exam. That doesn't make sense. So, but I am leaving it open because, I know many students have they've done 80% of a chapter, but they weren't able to get it done. And then they've got another section where they've done 85% of the problems, but they couldn't quite get it finished. So you're working hard. You're trying to learn the material for the test. This gives you a chance to go back and spend a couple more days if you feel like you're going to need those points to get those test points. Sorry, not test points, homework points in that homework grade. Get that homework grade up as much as possible, and then get your grade for the class. Because there will be a little bit of adjusting in the end, because I don't think this exam 2 score has showed up in the Canvas gradebook yet, which means it's not weighted right. Which means when I actually go to do final grades, your grade may fluctuate a little bit because I have to put the final weights on everything. So, if you're concerned, then you can work on your homework a little bit and get that homework grade up. Really, there's no reason not to have a homework grade in the 90s. It's just a matter of, because of the way the homework is set up, it's just a matter of did you do the work or not. So that gives you a little bit of chance to work on some extra homework there, especially since I know these last couple sections, well, especially the last chapter, is new for a lot of you. Some of you are not going to be able to get it done in the next 2 days, especially because you're studying for an exam. So this gives you a chance to try to learn that material. But sometimes what happens is students are so worried about homework points that they're doing homework they already know how to do to get the points, but they're doing that instead of studying for the test, and then they end up not doing as well on the test. And homework points are not worth as much as test points. So anyways, this lets you kind of strategize how you want to do it. Go in to learn the material, but then those last couple chapters I can still work on later and get those points there. Okay, so whatever strategy you think is going to work for you, you should do that. Okay, I think that's all the announcements I wanted to make. I didn't get any... I don't think I did. I don't think I got any emails asking for specific problems on how to do stuff. You'll have a couple problems from each of these chapters. There is, just like you'll see on the practice test. Actually, I don't want to go down that road. But anyways, you have a practice test. You can see what kind of questions I'm asking, that kind of stuff. Okay. Any questions about the test itself, how that's going to work? Everyone's comfortable with that? Okay. Okay, then moving ahead into Chapter 8. So Chapter 8's an interesting one. Chapter 8 can be confusing for people because it's very different than math that you've done in the past. It is sort of a new area of mathematics, but it is an area of mathematics that if you were continuing on through calculus, if you're someone who's going into STEM, basically, your math or your engineering or your science or something like that, these kinds of concepts are going to come up regularly, right? It depends on what you're doing, but for most people in STEM, you're going to see this stuff from time to time, and some of you are going to see it a lot, right? So if you go into computer science, just Chapter 8, you're going to use these ideas all the time. You're actually going to start to think like Chapter 8, right? The way that you do a for loop and a programming language is an iteration, and sometimes you're going to be adding things. Oh, well, that's just a series, and so these kinds of ideas are going to come up a huge amount. If you're in computer science, you're going to be doing this stuff multiple times a day, for the next 40 years or whatever. So, and lots of other people, even if you're in other areas of science, you're going to be doing this kind of stuff. And the truth is, now at this point, if you go into STEM, you can just expect you're going to be writing code for stuff. I've been out of grad school quite a while, but even back then, most people were doing something in terms of coding, right? Because you have to code stuff. I had to calculate, for the work I was doing, I had to calculate thousands of matrix multiplications, and those matrices would get bigger as we would go down the sequence, and they would get to where they were thousands by thousands. So no one's doing that by hand, but I could program a computer to do it, and then 4 or 5 days later, it spits out all the results that I need once it's done doing all these crazy calculations. So these kinds of ideas basically are going to come up, and I would encourage you, if you're going down that STEM route, just embrace coding now. Just get comfortable with it. You're probably going to have to do it, and it will make it easier when you do have to do it if you're sort of comfortable with it. But anyways, these are the concepts we're going to be talking about. So I've got, let's see, I've got the book here, and then also I've got some examples that we can go over. So 8.1 is about sequences and summation notation. So I maintain that the hardest thing about Chapter 8 is the notation, and that happens with some topics in mathematics, where the mathematics is actually not that hard, but the notation just freaks people out and they can't wrap their brain around it, and then they think, oh, this is really hard. Sequences and summation notation, once you get it, you go, oh, that's actually not bad at all. But it takes a little time to get comfortable with it and get used to it. We're not just solving equations. You know, that used to be kind of the buildup for a chapter. We'd learn about the behavior of a type of function, then we'd solve equations with it. This is sort of a deviation from that. This is getting into concepts that you use different than just sort of solving algebra, right? Those of you who are taking Calc 2, you're going to have a whole chapter on sequences and series. It's going to play a big role there, and you're going to do some much fancier stuff in there than we do in here. And here, we're really just getting an introduction. You're kind of dipping your toe into sequences and series and going, oh, okay, I kind of get what's going on. Those aren't so scary. And then you'll do some high-level stuff in Calc 2. Those of you who take a programming language at some point, you're going to be doing these kinds of ideas, these iterations and summations. You just do them all the time inside of computer science. And then, of course, if you're math, this kind of stuff's going to come up. So what is a sequence? Well, the thing is, a sequence is kind of like a function. And I know one of the reasons that people get confused about functions is because there's a bunch of different ways to view functions, right? You can view a function oftentimes as a graph. You can view a function as just a rule, f of x equals 2x minus 1. That's a function. You can view a function as a table where you have a column of x's and a column of y's. Sometimes a function can be written as tuples, right? Just a list of tuples that tell you what input turns into what output. So there's a number of different ways that your mind has to be flexible so that you can adjust from thinking about, sometimes you want to look at a function as a table. Sometimes you want to look at it as a graph, right? It can be helpful to look at the graph. So you want to be able to bounce around between those ways of thinking about a function. It's the same with sequences and series. We can sort of conceptualize sequences and series in a few different ways, and you do that based on whatever is the easiest way for you to visualize the particular problem that you're working on. So at its most, this is not the mathematical definition. This is just sort of the sloppy way that we would define a sequence. But you can think of a sequence as an ordered list of numbers, an infinite ordered list of numbers, right? So ordered, and that the order matters of a sequence. And infinite, so this book actually draws a difference between an infinite sequence and a finite sequence. As you sort of progress through your math classes, what you're going to find is usually what books do is they define a sequence to be infinite. And then if a sequence is finite, they call it a finite sequence. So when someone just says sequence, the implication is that it's infinite. Although we are sometimes lazy when we talk about these things, and we may say sequence when it's like a truncated sequence. It's a finite sequence. But usually you can tell from the context, right? It's like in everyday English, when someone uses the word or, well, there's two kinds of ors. There's the exclusive or and the inclusive or. But you don't normally stop and think about oh, is this person using inclusive or exclusive or? You just tell from the context what they mean, right? You sort of go, oh, I know the option they're giving me. So you go that. So it's the same thing here. When someone talks about a sequence, you're probably going to pull from the context of the problem, whether it's an infinite sequence or a finite sequence. But if someone just says sequence, the implication is it's probably infinite. But that's not the only way to think about a sequence is as an ordered infinite list, right? We have some other ways that can be very useful to think about sequences. And one is, like we were just talking about functions, one way to think about a sequence is as a function, because it actually is a function itself, where your domain is the natural numbers. So your inputs are 1, 2, 3, 4, 5, 6, 7, and your outputs are whatever that sequence value is. So sometimes it's convenient to deal with a sequence in its functional form. Sometimes it's not. It just depends on that particular problem that you're looking at, if we should view it this way or not. But it is helpful to understand that these things are functions, right? They're functions on the integer domain values. So for instance, there's a picture in here. Where was that picture? There's a picture in here somewhere. Where was that? Oh, like here. So basically, this is what you're used to thinking of a function as, right? Is a continuous function like this. Those of you who are going through calculus, functions are just going to get weirder and weirder for you up until you get your degree. We just come up with weirder and weirder versions of functions. But this is normally what we think of as a function, right? We kind of think of continuous functions. Well, imagine if you only took the points that were on the integer inputs, you'd get this. Well, that's a sequence right there, right? Your 1 comes in, gives you back a 1. Your 2 gives you a 1/2. Your 3 gives you a 1/3. So the inputs would be 1, 2, 3, 4. That's your domain. And your outputs are 1, 1/2, 1/3, 1/4. That would be the actual sequence. Okay? So that's one way to think about it. That's sometimes very useful in order to think about it that way. We don't have to think about it. It's like I say, it's like functions where we're going to pick whatever is the easiest way for us to visualize this, and we're going to go with that. Let's see. Make sure I do this in the right order. Okay, so what do we do for a sequence? Like here we've been given a formula for a sequence here. A sub n equals 3n plus 4. So what does this a sub n mean? Well, we can see up here, look at our sequence. It's a sub 1, a sub 2, a sub 3, a sub 4, up to a sub n, and then it keeps going. In other words, we have some sequence. We probably would call this sequence right here capital A, and then all the terms in it would be some lowercase a with a subscript. So that way you can tell what elements belong to what. Because what if you have a couple sequences? Well, if you have a bunch of lowercase a's and a bunch of lowercase b's, then you always know what sequence they belong to. One will belong to capital A sequence, and one will, the other ones will belong to capital B sequence. It just makes it a little easier to keep track of. But again, it makes the notation a little bit more complex. So we have some sequence A, and notice that the subscript tells you the term that it is in that sequence. So a sub 1 is the first term in the sequence A. A sub 2 is the first term. Sorry, a sub 2 is the second term in the sequence A. B sub 7 would be the seventh term in sequence B, right? So it's pretty easy to match them up. Sometimes I've seen books before, and we got rid of this book for lots of reasons, but some books, they number things like computer science does. Computer science has a weird way of counting. They like to count starting with 0. And I've seen one book do their sequences in series that way, and I do not like it. I guess as a mathematician, I always like to start counting with the number 1 if I'm counting things. Computer science people like to start counting with the number 0, but it makes it kind of weird sometimes. Like when I'm writing code, I feel like half my time, not half, but a bunch of my time spent is figuring out like, okay, this loop started counting with 0, so am I ending in the right place? Like you got to make sure everything lines up right. So our book does it the way I like, where the first term has a subscript of 1. It makes the math line up a lot better, in my opinion. But there's more than one way to do it. So what this, like if we look at this one, part A right here, a sub n equals 3n plus 4. So if you want the fifth term in the sequence, that would be a sub 5. That means that n is 5, so you'd plug 5 in here for n. So 3 times 5 plus 4, right? Over here on this one, a sub n, if you wanted the fifth term, so that'd be a sub 5, then you plug in 5 for n, and you get your n. You would simplify this, and you would get the fifth term in that sequence. Now, some sequences, just like some functions, you have a nice rule. Like when we had functions, if you just have f of x equals 2x minus 1, then it's very clear. Oh, any value I want, I just double it and subtract 1. So some functions have a rule that tell you what your output is. Some sequences have a rule that tells you what the output is. Some sequences do not. There's all sorts of different ways we can have sequences. So some are not predictable in a nice formula like this. So you can start to see how, I can see how depending on the type of sequence that I'm dealing with, I would have to view it differently because I'm going to have a different set of tools that I can use depending on, is the sequence well behaved? Is it kind of a pain? What am I trying to do with the sequence? It just depends. And what is this -1 to the n? You're going to see this a lot in sequences and series, and the reason that we do that is to oscillate the sign. So sometimes what happens is you'll have a pattern where you want an oscillating sign. You want a positive, then you want a negative, then a positive, then a negative, then a positive, then a negative, and that's how you get that oscillating sign, is by raising -1 to a power. Because whenever -1 is raised to an even power, then it just becomes 1. But when you raise -1 to an odd power, it becomes -1. So then all your even terms will be positive and all your odd terms will be negative. Okay, so that's all you have to do. And also you can do, if you want it reversed, what if you want your even terms to be odd and your odd indexed terms to be even? Then you could make this -1 to the n+1, where the subscript is, the power is n+1, because then, it's sort of shifting the odd or evenness of that. So that's how you get those kind of functions right there, and you can see it. You can see it right here. You see how their first term in that formula, they plug it in, they get -1/2, and then their second term is +1/8. The third term is -1/26. The fourth term is +1/80. So see how that -1 to a power is oscillating the sign in front. So you get positive, negative, back and forth. So that's where that comes from. Okay, so these are easy. All you got to do is just plug the value you want right in, and you get the output, basically. You're not always going to be able to do that. So let me show you a couple things here. So we'll come back to that. We will come back to that. Oh, actually, that's the thing I wanted to do, was the recursion down at the bottom. So recursive functions. These are things that everyone needs at different times, especially in computer science, right? So a recursive function is a function that's based on the terms that came before it. So the most popular one, I'm sure, well, I don't know anymore. People learn when they're growing up. But the most famous one is the Fibonacci sequence, right? So the Fibonacci sequence is very famous because it comes up in a number of places. The Fibonacci sequence is associated to the golden ratio, which comes up in a lot of different scenarios. It's associated to patterns that you see in nature, and you can look up YouTube videos where they look at the numbers of the divisions on a pine cone, follow the Fibonacci sequence, and all sorts of stuff like that. But the Fibonacci sequence is a recursive function. You get the future terms by evaluating the current terms under a certain formula. So and there's a couple of different ways you can write the Fibonacci sequence. Wait, what happened here? Oh, because I have a separate page. Okay, that was weird. I was looking at a different page and trying to figure out why this line wasn't showing up, but that's because I had something written on a different page. So here's one way you can write the Fibonacci sequence. You may have seen this. You can actually do the same Fibonacci sequence with a couple of different starting points. But we're just trying to focus on recursion in general. We don't care too much about the actual Fibonacci, but the point is you can come up with lots of different recursive functions and then evaluate them. Computers are really good at this because, what if we want to know the 100th term? We're going to have to calculate 100 terms of this sequence. It's probably better to just write a little computer code to do it for you in a couple seconds rather than having to do 100 calculations. But here's the idea behind recursion. You have a formula that tells you how to find the current value that you want based on previous values that came before it. And then you need starting points. You need enough values to be able to evaluate your formula one time. And then from there, if you've done it right, it should be self-feeding. It just keeps feeding itself, the formula. But if, like, I can give you the formula, but if I don't give you the starting values, you won't know what the sequence is. Or I can give you the starting values, but if I don't give you the formula, you're not going to be able to do it. So the Fibonacci sequence says if you want to know the nth term of the Fibonacci sequence, you take the two terms that came before it. So if we're at n, then that's n minus 1 and n minus 2. So like if n was 5, then n minus 1 is 4, and n minus 2 is 3. In other words, if we want to know the fifth term of the Fibonacci sequence, we're going to add together the fourth term of the Fibonacci sequence with the third term of the Fibonacci sequence. And you can see how that means you have to start from the bottom and work your way up. Now, those of you who are going into computer science, you'll actually learn there's some neat stuff you can do with recursion where, well, there's just some neat stuff you can do with recursion. So for us, what's this going to be? Well, our sequence would look like, let's see, where's the code here? So what would this look like for us? Well, we'd start with a sub 1 is 1, a sub 2 is 1. Okay, so now I'm going to plug those in. So I've got, to figure out a sub 3, that's a sub 2 plus a sub 1. Well, that's 1 plus 1, so the next term is 2. To get the next term, I add the two previous. Well, that's 2 plus 1, which is 3. Okay? Then to get the next one, I add the two previous terms. That's 2 plus 3. That's going to be 5. Then 8. Oops. Then 8. Then 13. And you can kind of just see it's going to go from there, right? You can keep literally going forever calculating. Oops, that's not the right command. You can go forever from there, right? So you could very easily, just with a for loop, you could write this into a computer, you know, for n equals whatever number you're trying to figure out. You know, you write some values, they're going to add together, they're going to rewrite themselves each time, and you're just going to get this running value. You can change this to be lots of different things, but you just always have to make sure you have enough starting values to sort of get this thing going. And then it's just this iterative process of you can get the next term in the sequence, next term in the sequence, next term in the sequence. Some recursive formulas you can actually mess around with and you can do some creative stuff with. We're not going to do that in this class. That's a little bit beyond the scope of what we're going to cover here. Some of you will do that down the road. But that's when you see a problem like this with recursion, all you're doing is you're taking your values over here and you're plugging it in over here, and you just keep doing that until you get to whichever one they asked you for, right? If they asked you, like for here, if we were asked to give the 9th term, then we would do this till we were 9 deep in our sequence, and then we would give our answer, okay? Let's see. Yeah, let's talk about the factorial before we talk about sigma. So the factorial, some of you are familiar with the factorial. Some of you may not have seen it before. It is a mathematical operation indicated by the exclamation mark. So in mathematics, you really never see people write things with an exclamation mark because otherwise they're going to think it's the factorial. So like, you know, if you're writing something, you put an exclamation at the mark to make it seem like, you know, emphasis or this is excited or whatever. In mathematics, it's literally a mathematical operation. And what it means is you take the number. So here we have n factorial, so that would be a number. Whatever that number is, it's that number, and then you keep subtracting 1 all the way down till you get to the number 1, and you multiply all those together. So the definition of n factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5, all the way down to 3 times 2 times 1. So for instance, 5 factorial is 5 times 4 times 3 times 2 times 1, and multiplying by the 1 doesn't obviously change it, but it, you know, it's just part of the pattern, so it's nice to write it in there. You know, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Now the thing about factorials is they get huge quickly. Like they get huge in a way that is alarming and sometimes difficult to deal with. So here's your, over here on the left, let me move this over here. Here is our factorials from 0 through 20. So you can see the factorials start kind of small. Oh, important point, 0 factorial is equal to 1. I know it does. That's not, you wouldn't think so. Those of you who go on to study combinatorics, you'll see why mathematics has defined 0 factorial to be 1. It actually does make sense that 0 factorial should be 1. But right here, when we're just getting used to factorials, it seems weird. It seems like 0 factorial should be 0, right? But it isn't, and there's good reason why we don't do it that way. So just know that, because sometimes what'll happen is you start doing permutations and combinations, and then you have factorials in your denominator. And if you think that 0 factorial is 0, then you're gonna have problems, right? So make sure you know 0 factorial is 1. But look how big these things get. 20 factorial has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 digits. So 20 factorial, that's not a very big number. 20 is not a very big number. 20 factorial has 19 digits in it. So these things get massive very quickly. My area of research in grad school was combinatorics. I did a lot with graph theory, and I would work on stuff where they would blow up at this kind of rate, which makes it hard even for a computer to do. Like, it's like you have computers running these programs for you, but a lot of times if you have factorials in there, it's like you sit there and you calculate, okay, at this rate, my calculations will be finished in 10,000 years. Okay, well, that's not going to work, right? So factorials can be problematic in that way, that they get very, very big very quickly, and it doesn't take them very long to get too big, even for a computer to not be able to compute them a lot of times. So like if you have a TI-84 calculator, which are great calculators, and you put in like 80 factorial, it's going to use up all its RAM, and it's going to say, sorry, we gave up, can't calculate it. So so just be aware of that. There's difficulties you run across when you're using the factorial. Now, there is some kind of interesting things you can do with the factorial. In fact, I mentioned some of the drawbacks of the factorial. But like here, right here, this is a problem. If you try to put this in most calculators or computers, maybe if you're dealing with a heavy hitter computer algebra system or something, it might be able to calculate this. But if you're dealing with a TI-84 or something like that, it's not going to be able to simplify 200 factorial over 195 factorial, because computers are dumb, believe it or not. Like, most people think computers and calculators are smart. They're not. They're dumb. They do a bunch of additions, subtractions, multiplication, and divisions following directions endlessly. So when you tell the calculator to do 200 factorial, it tries to calculate that number, which, as we saw from Blitzer, is a massive, massive number, and it's going to run out of memory before it can even get there, right? But you can do some algebra, which is a little bit more clever if you're trying to do something like this. So what you want to recognize is that there's the following pattern. Let me see, where do I want to write this? Right here. And that is that, let's say we have 5 factorial. Well, you should recognize, where's that going to show up? Oops, I wanted it down here. So 5 factorial is 5 times 4 times 3 times 2 times 1, right? But you could also think of 5 factorial as being 5 times, it's 5 times 4 factorial, right? If you take 4 factorial and you multiply it by 5, you now have 5 factorial, which you could calculate and go, okay, that's 120. But we can manipulate the algebra a little bit, which means you can separate out those multiplications when it's convenient for your algebra. So why would we do that? Well, if you think about these numbers right here, 200 factorial is 200 times 199 times 198 times 197 times 196 times 195 factorial, right? So for instance, this, let me write that out in case you didn't catch all that. So this is still 195 factorial on the bottom, but on the top, let's see, 299, 98, 97, 96. So this is 200, 199, 198, 197, 196. So see if that makes sense to you, that 200 factorial is 200 times 199 times 198 times 197 times 196 times 195 factorial. And it's all multiplications, so we can do our simplifying as we want. And then we can just cancel these 195 factorials because everything's multiplication. There's no additions or subtractions going on here. So we're perfectly clear to divide out 195 factorial from the top and bottom. And what are you left with? You're left with 200 times 189 times 198 times 197 times 196. So that's easy. You can just throw that in your calculator and get an answer. And you've now simplified this thing that your calculator doesn't know how to simplify. Right? It just does sort of the dumb brute force process, and it runs out of resources. But you are much more clever, and you can go, well, I think there's a better way to simplify this. So that's a nice little handy tool for simplifying factorials when they come up. Okay. Right, and here's some example factorials right here for you. So you'll see they'll start using this factorial notation in your sequences and stuff like that. So like here's an example where we've got the nth term of this sequence is 2 to the n over n minus 1 factorial. And then you're just going to calculate those when you calculate the terms that you're dealing with. So nothing real tricky going on there. So, you know, whichever term it is that they say they want. Let me just double check I have not skipped anything I wanted to say here. We got that. Okay, good. Yeah, okay, good. Then we get to summation notation. So this is a thing that is confusing for a lot of people because it's a brand new symbol and people are not familiar with it. It's this thing that kind of looks like an E a little bit, like a capital E, but maybe not so much. It's just another Greek letter that we use for stuff. It's capital sigma. Lowercase sigma gets used for quite a bit of stuff, especially in statistics, and those of you doing high-level math, we oftentimes use sigma for function names. This is capital sigma, and in mathematics, it always means add stuff up. Well, 99% of the time. You might have someone write a paper and they use it to mean something else, but generally, capital sigma means add things together. All right, so whenever you see that, you go, oh, I'm supposed to add some stuff up. And you're adding it together in an iterative manner. You can have a finite sum where you sum from n equals 1 or whatever to some other number, or you can have them go on to infinity. And those get a little bit trickier, so we'll circle around back to that in a little bit. But right now, just sort of try to focus on the understanding what we're looking at. This symbol means add things together. The things you're adding together over here on the right, okay, and you go, oh, well, what's n supposed to be then? N comes from the iteration where it goes from whatever value is given on the bottom to what's given on the top. So like I say, here we would be doing an infinite sum, which is called a series, right? That's all a series is. The difference between a sequence and a series, they're both infinite lists. The series is where you add all the terms up. The sequence is where you just leave them as a list of terms. So an infinite list of terms is a sequence. If you add up the terms in that sequence, it's called a series. Okay. So let's change this to another way that you might see it sometimes. Oh, here we go. So let's say we just have it be like, actually, before we do that, I want to show you some stuff. So what we would do then is you iterate on n, right? This is why those of you who are familiar with any kind of programming language, this will seem familiar to you, because that's what you do with loops. You're just iterating on something again and again and again until you've finished your problem. So n starts at 1. They give you the starting value down here at the bottom. N doesn't have to start at 1. Very frequently, n will start at 0. Very frequently, n will start at 1. But you will also run across cases where n starts at 4 or 7 or 25 or whatever. There's no reason it has to start at 1 or 0, but it's usually a little simpler. So a lot of times when we're writing our series out, it's kind of nice to have them start at 1 or where your n starts at 1 or 0, but it's not necessary for that to be the case. So n starts at 1, And then each time you do the process, you iterate 1 to be one integer greater. So our n would start at 1. I would plug n in here for 1 and go, okay, 2 times 1 is 2, right? So then we start getting our terms, right? So you can see when I plug in 1 for n, I get 2 times 1, which is 2. So our first term is 2. Now I'm going to iterate and up my n by 1 value. So now n becomes 2. I plug 2 in here. 2 times 2 is 4. My next term is 4. Now I plug in 3. 2 times 3 is 6. So my next term is 8. What did I say? 2 times 3 is 6. Then 2 times 4 is 8. 2 times 5 is 10. 2 times 6 is 12. So you can see our n is going up by 1, but each time we're multiplying by 2. So our terms become the doubles of those things. And then that summation means add them together. So if we had a running sum, we would go, okay, our first sum when I plug in n equals 1 is 2. So the first thing I get is 2. Then the next thing I get when I plug in the 2, I get a 4. So remember, we're adding things together. So I get the 2 I got in the first term, the 4 I got in the next term, that's 6. So now our running sum is a 6. Then I would get n equals 3. Well, that's a 6. So we already had 6, and now I'm adding 6, so now our sum is 12. So you just keep adding it up. And in the end, you don't have a sequence of sums like I have it written here. This is just so you can see as I'm going along how I'm adding these terms up. When you're asked to simplify this, it's just whatever your end result is. It's some number that you're giving at the end of the process, and it's the total of all the terms in your sequence. Okay, so we'll return to the infinite series in a minute, but let's simplify this down to like 6, because I think that's actually what we have here. So we'd go, okay, I would take the numbers, I would plug them in here one at a time until I got to 6. Let's get rid of the dots. Okay, so we'd go, so this says we're going to start at n equals 1, and the way we're going to stop is when n equals 6, that's our last step. Okay, so I go n equals 1, I plug it in here, I get 2. Plug in 2, oh, I get a 4. Plug in 3, I get a 6. Plug in 4, I get an 8, then a 10, then a 12. Now I'm going to add all those together. So those should all add up to 42. So our final answer wouldn't be this sums list. At the end, I would just write equals 42. Okay. So that would just be your answer. Oh, if you were given this, you'd just go, oh, well, that's 42. Okay, so you'd have your running total. Now you can adjust these. You can play around with these. We could take the same amount and we could start at n equals 0 and end at n equals 5, and we would just adjust this to be 2 times n minus n plus 1. And we could get that same sum, but I don't think we really do much of that in here. But that's the bottom line, is this sign just means add stuff up, add it together. Okay, so we'll revisit that in a few minutes here. Yeah. Okay, so we got those. Okay, yeah, I think that gets us 8-1. So we have two real basic types of sequences that come up a lot in mathematics and science, and the tools for dealing with those are generally simplified. Hold on one second. I gotta have people bringing in the dog. He keeps barking and it's distracting to me. All right, let's see if a family member will bring the dog in for me. Where was it? Oh, right. So there's two types that come up. You're going to see, those of you who go on to Calc 2, you're going to see more complicated sequences and series. But at that point, by the end of Calc 2, you're also going to have a much larger tool set for dealing with those sequences in series. Here, we're really just prepared for dealing with arithmetic and geometric sequences in series, and sort of making sense of those. And so that's what we're kind of going to focus on. But just be aware, that's not the whole world of sequences in series. That's like barely scratching the surface, but it's what we're able to look at right now with the tools that we have learned to this point. So let's see, where's A2? So what I'm going to say is this can get a little bit confusing. So before you do any problem in this chapter, always try to identify, am I dealing with an arithmetic sequence or am I dealing with a geometric sequence? Because the tools we use for those are separate. And then there's going to be a few different formulas for each of those. Now the good news is they're all here in blue in the book. So if you get confused, all you got to do is open the book and go, oh, that's right, that's that formula. Because they're formulas that actually make sense. We don't have the time to go through and derive them. In the old days when we were in the classroom for all the time, we'd like derive this stuff out. And then you can kind of make sense of it. But we just don't have the time right now to get through that. So I'm going to define these for you, but I highly encourage you when you get confused or whatever, look for these blue boxes in the book because they are going to have your answer. And then also look at the examples that are nearby because the mathematics for any of these problems is not very difficult, but you need to know the formulas and stuff like that in order to carry it out. So an arithmetic sequence is a sequence in which each term after the first differs from the preceding term by a constant amount. The difference between consecutive terms is called the common difference of the sequence. So in other words, if you take two consecutive terms in the sequence and you subtract them, you will get the same number as if you take any other two consecutive terms and subtract them. It's the same amount. So like you can see this sequence right here. How did we get from the first to the second? We added 4. Add 4, add 4, add 4. So that's what an arithmetic sequence is. You just keep adding the same number again and again and again, and that's how you get that sequence. And this makes sense. I mean, we can model this pretty easily. If I have a lemonade stand and I'm selling lemonades for $2 a piece, then every time I sell a lemonade, another $2 ends up in my money box, right? So if you look at the sequence of money in the money box over the course of the day, it's going to be 0, 2, 4, 6, 8, 10, 12, 14, because every time I get $2, I put it in the box. A lot of financial stuff is actually calculated using sequences as well, because you'll say, okay, each year you're given this much interest, and then that gives you the amount in your account at the beginning of the next year, and then you just sort of keep doing your compounding that way. Actually, that wouldn't really be an arithmetic sequence, and that would be more probably geometric sequence. But you get what I'm talking about, like where a lot of financial stuff is computed in steps, and so we can represent it with a sequence or a series depending. Okay, so lots of these. So your common difference can be a negative number. That's totally allowable. So we talk about how you're adding the same thing every time, but you could be adding a negative number. So look at this, 8, 3, -2, -7, -12. What you're doing is you're adding -5 to each term to get the next term. Okay, so that's all an arithmetic sequence is. And you can write them out. So, let's say you're asked to find the 12th term of this arithmetic sequence. Well, you could figure them out in a row, but what if you don't want to figure out every single term along the way? What if someone asks you for the 1234th term in a sequence? Well, you don't want to figure out all the ones in between. Well, here's your formula for the general term of an arithmetic sequence. So the nth term of an arithmetic sequence with first term a sub 1 and common difference d is given by the following. So if I gave you a problem and said, okay, your first term in the sequence is 5 and your common difference is 12, and I asked you for the 10,000th term in that sequence, then you'd say, okay, a sub 10,000 is equal to, I should have written them down. I forgot which numbers I said. Did I Did I say 7 and 12? So if our first term is 7, then you just plug that in here for a sub 1. We said we wanted the 10,000th term, so you plug that in here for n. And if the common difference is 12, you just plug that right in here. So the math is easy. It's just multiplications and additions, but it's sort of understanding where each piece goes in that formula and when to use this. So you can see here's an example right here. Find the 8th term of the sequence whose first term is 4 and whose common difference is -7. So they just use this formula right here. They put it down here. So you plug your 4 in for a sub 1. Your n is 8 because they want the 8th term, so that goes in here for 8. And then your d is -7. They tell you that's the difference. So you get all that, and you go, oh, -45. So you don't have to calculate every single term in between. You can, but frequently that's like the long way to do it. This is a pretty easy formula to use, so I would encourage you to have that, you know, when you're doing the homework, sort of be ready to flip to this page and go, what was that formula again? And it kind of makes sense because what's happening is each step you're adding a certain amount. So it makes sense that what we're adding is a multiple of that amount. We're adding a multiple of it's the number of steps that you take to get to the term that you're interested in times the number that you're adding every time. So actually, this is one of those sequences where if you understand what's going on, you don't even have to memorize it. You just go, oh yeah, it's the first term plus however many steps I need to take to get to that last term, and each step involves adding d, so I'm going to multiply by n minus 1 times d. It actually makes a lot of sense. So, you know, keep that in mind. Okay, sometimes we might want to sum the first n terms of an arithmetic sequence. Now, I talked before, I sort of hinted at the fact that we're going to talk about a series, and a series is where you add up an infinite number of things, right? Well, with an arithmetic sequence, you can't add up an infinite number of things because what's going to happen is it's going to go to infinity, right? If you're adding up the same number every single time, even if it's really, really tiny, 0.00001, if you add enough of those, you get to 1 and 2 and 3 and 4 and 5, and it goes towards infinity. So it doesn't make sense to add up an infinite number of terms in an arithmetic sequence, but you may want to add up a finite number of terms in an arithmetic sequence. You may want to add up the first 20 terms of an arithmetic sequence, or maybe even the first 1,000 terms of an arithmetic sequence, and you don't really want to do that by hand because, I mean, if it was short, you could, but it gets to be a pain if you want 1,000 terms, right? So we call this S sub n to be the partial sum. So it means the S is for sum, and the n is telling us the finite nature of that. So it's saying add up the first n, right? And here is an interesting way where you can actually see where the formula comes from. So what they do is they take S sub n is equal to a1 plus all the terms up to an, right? And then what you do on the line before that is you just flip everything around. So now we're starting with a1 on the right, and we're getting bigger as we go to the left. So what happens for every single one of these terms, when we add up the columns, you get a1 plus an. And how many of those do we have? N, right? Because there's n of these. So we have n, a1 plus a sub n's. So when you add, so you have this, n times a sub 1 plus n. So what you're going to do, but that's actually 2 of the sequence because we've added the sequence up twice. So that's where this comes from. 2 s sub n equals n times the quantity a sub 1 plus a n. Well, if you divide both sides by 2, you have your sum. The sum is n over 2 times a sub 1 plus a sub n. So that's awesome. That means this is a really easy formula to do. All you need is your first term, your last term, you add them up, and multiply by n divided by 2. And you go, but wait, what if I don't have a sub n? Well, we just looked at that, right? We just gave you that formula a second ago. Oh, was it the same page? Wait, where did that other formula go? It's this formula right here. Use this to get your a sub n. And then once you have a sub n, you should know a sub 1, then you can figure out the sum of the first n terms. So it's actually very easy mathematics going on as long as you understand, oh, I first have to use that other formula to get a sub n. Now that I have a sub n, I can figure out my sum. Okay, but the actual like calculations are easy to do. It's the logic that you have to piece together to make sure you understand. So here's that formula. So that one's pretty straightforward. You know, this stuff takes a little bit of practice, but once you get the hang of it, it's not bad at all. Oh, is that all I was going to say? Yeah, there's not a ton to do with arithmetic sequences because they just kind of are what they are. There's nothing real like hidden or fancy about them in general. And then we get to geometric sequences in series, and here's where you start doing things that are a little bit more powerful. And you're going to see, like here they offer, there you can see if you read this, they're talking about one company offers $60,000 the first year with increases of 6% per year for 4 years after that. The other offers $62,000 the first year with annual increases of 3% per year after that over a 5-year period. Well, you could model those examples by a series, right? So you'd have, okay, here's what I'd make in the first year, second year, third year, fourth year, fifth year. You add them all up. That tells you how much money you're going to make in the first 5 years. If you do that for both of these job offers, then you can see, oh, here's how much I'll make in the first 5 years total at this job, job A. Here's how much I'll make total in 5 years at job B. And then you can decide, oh, well, this one's significantly better, or it's not as good, or whatever, right? So you can go from there. So here's some examples of a geometric sequence, right? So a geometric sequence is a sequence in which each term after the first is obtained by multiplying the preceding term by a fixed non-zero constant. The amount by which we multiply each time is called the common ratio of the sequence. So basically an arithmetic sequence is obtained by adding the same thing to each term in the sequence. A geometric sequence is obtained by multiplying each term by the same thing in the sequence. Okay, so here's an example. 1, 5, 25, 125, 625. Well, we can see, yep, we're multiplying by 5 each time. So the common ratio is 5. And it's really easy to find the common ratio. All you have to do is take 2 consecutive terms and divide, because that's how you got the next term, was by multiplying. So if you want to work backwards, just divide, and then you'll get whatever that common ratio is, because sometimes it's not obvious. And look here, see how we get that oscillating? 6, negative 12, 24, negative 48. The common ratio there is negative 2. So you can still get that oscillating behavior. And look at this, fractions are fine. In fact, fractions are a lot of times like helpful. 9, negative 3, 1, negative 1/3, 1/9. Our common ratio is negative 1/3. So not only can they be fractions, not only can they be negative, they can be negative fractions, but the good news is, once you've wrapped your brain around how these things, like the definitions of these things, that's not even going to bother you that the common ratio is a negative fraction. It just doesn't really make much difference. So don't psych yourself out about it. And then they bring up a little point here, which is kind of interesting. A geometric sequence with positive common ratio other than 1 is an exponential function whose domain is the set of positive integers. So you're essentially just getting the integer values of an exponential function. But right, so here's another one of those blue boxes. So remember we had a formula a minute ago for the general term of an arithmetic sequence. Here we have the general term for a geometric sequence. So what if you want to know the 75th term in the sequence, and you don't want to have to write out the 74 terms that come before it? Well, what you do have to do is analyze and figure out what your R value is. That's your common ratio. And we saw that was easy. Just take, whatever, 2 consecutive terms. Take the third term and divide it by the second term, and whatever you get, that's your common ratio. Or take the 7th term and divide it by the 6th term. That's your common ratio. So the common ratios are not hard to find, right? You just divide by the 2 consecutive terms that you have there. A1, these things can start anywhere. Your first starting term does not have to be R. Sometimes people think it has to be like say we started back here. See how this one we went 1, 5, 25, 125, 625. These are kind of like powers of 5, right? This is 5 to the 0, 5 to the 1, 5 squared, 5 cubed, 5 to the 4th. They can be like that, but they can also be like this, where see how our 6 is not a power of -2, our common ratio. So your starting term and your ratio can be separate from each other. Sometimes people think they have to match up and be the same. They don't. But your common ratio has to be consistently the thing you multiply to get the other term. So with that said, you just take your first term and you multiply by r to the n minus 1. It's kind of like what we did before when we broke down the arithmetic sequence and said, well, it makes sense. You take your starting point, a1, and then you add enough of your common difference to get to that value you care about. Well, we're doing the same thing here. You start with your initial term and you multiply by r until you get to the term that you would care about. So this formula right here just gives it to you. So you can see here's an example. Find the 8th term of a geometric sequence whose first term is -4 and whose common ratio is -2. Okay, well, we want to know a sub 8. So our first term is -4. So I put that in here for a sub 1. And the common ratio is -2, so I put that in there for r. And the power that I'm raising it to is n minus 1. Well, our n is 8. So 8 minus 1 is 7. So it turns out the 8th term in this sequence is 512. See how we didn't have to find the 7 terms that come before it? That's convenient, right? So, so that's how you do that. Excuse me, my throat's getting sore from talking so much. Okay, let's see. Then I wanted to talk about this is a little bit in here on Ponzi schemes and geometric sequences. This is generally where, Ponzi schemes will go on sometimes for a long time and they can make incredible amounts of money, but eventually they collapse at some point because the amount of money that is owed is so great that you kind of can't hide it anymore and it comes to light. So, if your R value in a geometric sequence is large, then your values will grow very quickly. Okay, then we have the sum of the first n terms of a geometric sequence. I'm not going to go over the derivation, but it's pretty straightforward. So if you were someone who wanted to follow this, you kind of, it's not very difficult to follow. You start with your sequence, you multiply both sides by r. So I guess I am going through it. Multiply both sides by r, then you subtract off. You subtract these two things, s sub n and r s sub n, to get this thing on the left. And notice you get all these middle terms canceling each other out. So you just end up with a sub 1 minus a sub 1 r to the n. Factoring this using the binomial theorem gives you this. No, we didn't. I was thinking of something different. Factor the a sub 1 out, and you get 1 minus r to the n, but we have that on the left. So then we divide, it's just 1 minus r, not 1 minus r to the n. Divide by that, and you get this term right here. So here is your sum of the first n terms of a geometric sequence. So if that's what you're trying to get, that's your formula right there. So you'll probably have to find this blue box when you're doing the homework to make sense of, how to do those problems. But it's really just identifying the r and all that kind of stuff and plugging it in. And your common ratio, let's see, the sum s sub n of the first n terms of a geometric sequence is given by the following formula, in which a sub 1 is the first term and r is the common ratio with r not equal to 1. Oh, right, because you see you'd get 0 in the denominator if r was equal to 1, and then your formula isn't going to work. So just make sure r isn't equal to 1. So a problem like this, you could do by hand. We did an example like this. You'd start with, when I did the example, I was using n, and sometimes in the book they use I. It doesn't matter. You will see that very frequently summations are done with I, and very frequently they're done with n. Also very frequently they're done with k and j. You see those letters a lot. Those are probably the big ones. I, j, k, and n. Sometimes you'll see A and B. So don't get worried about the letter. The letter doesn't matter as long as you're consistent and it tells you what to do with that in the formula. So it tells you what to do with the I, then you're fine. Technically, you don't even have to have an I in there, but then you're just adding a bunch of constants. Like if it was just the sum from I equals 10 of 6, you would just be adding a bunch of 6s. Right? But in this case, it's 6 times 2 to the I, so you have some calculations that you have to do there. But you can see they just go through, plug it into the formula, and then go. So use this section of the book a lot. Oh, what do we got? Someone going on here. Let's see. Let's just get rid of that there. Sorry, I didn't see that we were getting spammed with some stuff we don't need there on the YouTube stream. That hasn't happened in a couple years since like first started teaching these online classes. Okay, so yeah, use the book to find if you're confused about a problem, find a similar problem in the book. There will be one. Find the problem in the book and look at how they solve it, and then go to the blue box and find the formula that is corresponding to that problem you're doing. And like I say, none of the math in this section is like, and when I say the math, I'm talking about the actual calculations. The calculations are easy. They're like additions and multiplications and a couple powers, but you're not going to be able to do them if you don't know how to use those formulas. So look at the examples, look at the formulas, and you should be fine. So here's a money one. We're not going to work through it, but you can get an example of how that works for money. Annuities, we're not going to talk about annuities either. If you're interested in annuities, go ahead and read up on it. You can make sense of it all. But you can see here's a formula for annuities. Here we go. Here's what I was looking for. Geometric series. So here's where things start to get weird. So you're going to notice as you progress through your mathematics, infinity comes up on a regular basis, and every time it does, it's going to get weirder and weirder. Those of you go on to Calc 1, infinity gets weird in calculus, right? And that's just the beginning of the weirdness that infinity can do. I mean, all the way literally, like you get to your upper division, and infinity's going to play other weird roles depending on what you're looking at. And here is an idea that a lot of times people get uncomfortable with, is that you can add up an infinite number of things and have it add up to a finite amount. Okay, that seems weird. Like, if I add up an infinite number of things, aren't I going to get infinity? And the answer is, well, first of all, when you add things up, you don't actually get infinity. But it can go to infinity, where each time they just keep blowing up to a bigger and bigger number. Or what you can get is, as you're adding things together, they get closer and closer. In Calc 1, you'll call this a limit. As you get closer and closer to something, you actually approach a sum. And this was first, the Greeks were first thinking about this, and the idea was this. I forget who it was. That's one of the names you probably have heard before. I forget. But they put forward this thought experiment. What if I'm standing some distance from a door, okay? And then I decide to embark on a journey where I'm going to walk to the door. But the way I'm going to do it is every time I take a step towards the door, I'm going to go half the distance to the door. So if I'm 10 feet away, then my first step gets me 5 feet from the door. Then my second step gets me 2.5 feet from the door. And then my next step is half of that. And you can see we're just halving it each time. We're cutting it in half. And the answer, and then the question that they didn't quite understand then, because they didn't have calculus in order, you'll learn the calculus tools to figure this kind of stuff out. But the idea was, well, how can I be walking forever but never reach the doorway? Because if I'm only ever getting halfway to the door, then there's no step at which I'll reach the door, right? Because even when I'm 1,000th of an inch from the door, well, my next step, I'm 2,000th from the door, right? And then I'm 1/4,000th from the door, and then 1/8,000th from the door of an inch or whatever. You never actually get to the door. And that's that idea that we're looking at, is we can keep adding up these numbers and get a finite value. Because if you think about all these steps I'm taking towards the door, if I started 10 feet from the door and every step I have my distance to the door, then the sum of the distance that I covered is getting close to 10, right? Because I'm almost at the door, but I'm not quite there. I'm just a little distance from the door, but it's pretty close to being 10 feet that I covered. And that's the idea, is you can add up an infinite number of steps, and they can add up to a finite number, but it's necessary for those numbers to be shrinking in a very special way in order for the whole sum to not just blow up towards infinity. And that's what we have to kind of think about. You can even come up with sequences where the numbers are decreasing, but they're not decreasing fast enough, and so your numbers still blow up towards infinity. If you take 1 over n, and you just keep adding the numbers 1 over n, you will not get a finite sum. They will blow up towards infinity. But if you take 1 over n squared and you add up those numbers, they will add up to a finite number. So it's kind of weird. You get like two very similar sequences, but we call that converging. The one that adds up to a finite number, we say converges. The one that goes towards infinity diverges. That's the language you'll use in calculus. And actually, I think we use it a little bit in here. I'm trying to remember if we use that terminology or not. I didn't look that up this morning. I just was looking at the examples, so I forget. But so we can have what's called an infinite geometric series. We can add up an infinite number of things and get a finite value, but those numbers better be converging. And we're talking about all positive. So I'm not talking about that case where the numbers were, you have a positive, then a negative, and a positive, then a negative, because then you can play other types of games. But here we're talking about all positive values, an infinite number of positive values adding up, equaling a finite number, which is weird at first when you first start thinking about it. So here is the conditions. The sum of an infinite geometric series. So if r is between -1 and +1, so another way of thinking of that, and how you'll see this sometimes, is the absolute value of r is less than 1. Then the sum of the infinite geometric series, a sub 1 plus a sub 1r plus a sub 1r squared plus a sub 1r cubed. Because remember, that's how you get the next term in the sequence, is multiplying by r. So this might seem weird where you go, why do they keep putting a sub 1 in there? Well, a sub 1 times r is a sub 2. A sub 1 times r squared is a sub 3. A sub 1 times r cubed is a sub 4. That's how you get those terms. And look how easy this formula is. Look at that. How convenient is that? In which a sub 1 is the first term and r is the common ratio, the sum is given by a sub 1 over 1 minus r. Doesn't get much easier than that as far as formulas, right? Now notice the difference. When we talked about an arithmetic sequence, we had a subscript on our s to mean the finite sum. This s means the sum, the infinite sum, right? Of all the infinite numbers added together, you get the answer from this formula right here. So let's look at an example. Find the sum of the infinite geometric series. This one is oscillating, so we notice that. So what do? You take any term you want, and you divide it by the previous term, and you're going to get your r value. So if we take -3/16, okay, great. There's a question. I'll look at that in just a second. -3/16 divided by 3/8, right? Then we're going to get what? We're multiplying by -1/2 each time. So to get from 3/8 to -3/16, you multiply by -1/2. To get to the next one, -1/2. Next one, multiply by -1/2. So we're adding these together, and you can see that, oh, that's what they did here, the division, and you get -1/2 for your answer, or for your r value. So then you stick your r value in here. Remember, the bottom is 1 minus r. So 1 minus r. And our first term was 3/8, so you put that on top. So look at this. This is just, I mean, sure, it's a complex fraction, but this is not like a complicated thing to try to simplify. It's like pretty straightforward. You get 1/4. So all of these numbers added together, if you add up the infinite list of these right here, you'll get 1/4. So if you added up like 50 of them, you'd be really close to 1/4. If you added up 1,000 of them, you'd be even closer to 1/4. If you added up 1 billion of them, you'd be really, really close to 1/4. And if you add up an infinite number of them, you get 1/4. Okay, great. Let's see. A couple questions. Is the term on the top of the capital sigma the amount of terms we are calculating? Oh, okay, good question. Is the term on the top of the capital sigma the amount of terms we are calculating? Not necessarily. So let me read the rest in case it's connected. Is the n equals a under the capital sigma? Okay, good. So that's a good question because I know the sigma notation. I know it confused me when I first started learning it. My teacher ran out of time and he just told us to go read in the book and figure it out, which was a little confusing. So the way the sigma works is the number that you're iterating over, it tells you on the bottom what to start with. So you start with n equals 1, and then you just plug it into whatever your formula is, and the number on top is where you stop. So the n's that we use to simplify this, we would use n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. And when we hit n equals 6, that's when we stop. We do that last step, n equals 6, and then no more. We're done. So this tells us there should be 6 steps. And the n over here, it tells you what to do with the n in the formula. So here when n is 1, we would put 1 in for n, and then we would just do the calculation. So like if we're over, let's see, because we haven't looked at a sigma for a little bit. So I'm not sure if that answers your question, but the numbers above and below the sigma, they tell you the starting and end point of your iteration, right? So the one on bottom tells you where your iterator is starting, usually going to be 0 or 1, but it doesn't have to be. It could be 4. And then the one on top tells you where to stop. So we could do a problem where we look at we could do one like this. Let's see. N equals 3 to say 7. So if we did one like this with sigma, our n value would start at 3, and we would plug in an n of 3, an n of 4, an n of 5, an n of 6, an n of 7. And once n is 7, we do that step, and then we stop. We don't go on to n equals 8. So the values above and below sigma tell you the start and end points of whatever letter it is that you're iterating over. Is the n equals a under the capital sigma what we begin multiplying the term? It won't necessarily be multiplying, but yeah, the number under the capital sigma tells you where the starting point for that sigma. That's right. It sometimes will be multiplication. Sometimes you'll be adding it. You do different stuff. Okay. So you can see the formula for your infinite sum is actually really easy, but do be careful. Make sure that your R value is proper. I see people that just plow ahead. They might have an R value of like 3/2, and then they use that formula for S, but your R value won't converge unless R is between -1 and +1. So always double check that. In our case, we were fine because our R value was, what, -1/2? So we were fine. You can do an interesting problem here. This comes up occasionally. What if you have a repeating decimal? As you go further in math, you're going to realize that, like, a lot of people like decimals because they look really scientific and they look really fancy. But decimals are oftentimes a pain to deal with because you get this you get this inexactness, you get this rounding, right? Those of you doing computer science, you're going to learn, with floating points, you get these like rounding errors and stuff like that. So sometimes it's just better to deal with things in fractional form. So we can turn a number like 0.7 repeating into a fraction. So how do we do that? Well, 0.7 repeating is 0.777777 forever. But if you think about it, that's 7/10ths plus 7/100ths plus 7/1000ths plus 7/10,000ths. And you might go, wait a minute, where are you coming up with those fractions? Well, this is the tenths place, and there's a 7 in it, so that's 7/10ths. This is the hundredths place, and there's a 7 in it, so that's 7/100ths. This is the thousandths place, and there's a 7 in it, so it's 7,000. You get the pattern. So if you add up all these fractions, well, look what we have. We have an infinite sequence of numbers that we want to add together. All right, well, what do? You go, okay, well, we have that infinite series. My first term is 7/10ths, so I put that in the top of my formula. And what am I multiplying by to get successive terms? 10, 1/10, 10 in the denominator, sorry. 1/10 is what we're multiplying by each time, so that goes in your R on the bottom. Simplify the whole thing, and you get 7/9. So 7/9 is equal to 0.7 repeating. But in many cases, 7/9 is going to be a lot nicer to deal with than 0.7777 repeating, right? It's just, depending on what you're doing, it could be preferable to use 7/9 over that value. So there's lots of ways in which these sequences and series pop up. Like I said, they come up in finances, they come up in computer science, they come up in all sorts of stuff. Okay. And then that's 8.3. So I know it's kind of a new topic, and I know it's kind of a lot to take in quickly, and then you have a test in a couple days from now. So just try to, here's the key. If you get comfortable with the notation, you will be okay with the math. Right? If you can piece it all together and you can separate in your brain, here's arithmetic sequences, here's geometric sequences, and you understand the difference, and you learn those basic formulas, and you know when to use them, the math is fine. But that's kind of the hard part, is making sense of the notation and getting to where, you know, the notation does not intimidate you, and you just got to work through those examples. And with the sequences and series, if you're ever stuck, just start writing out some terms and try to make sense of it along the way. Like, make sure the formulas are making sense to you as you use them, and then the actual mathematics should be fine. Oops. I just spilled my water here. Okay, and then that wraps up. That's all the material for the course. So we have now learned all the necessary material that is required for this course. So just as a reminder, a couple things. There's the last discussion, easy 10 points. Please make sure you don't forget to do that. Check out the practice test, see what you think of it, and then make sure that you can take that exam and that you're all set up for that and that you're all ready to go, and that you could either submit pictures of your work or a PDF scan of your work or something. But I have to go through and verify that, yes, this person actually did the work. They weren't just using some cheat to get the answers to their problems or something. Okay. And I trust all of you. You're actually a great class where people tend to be working hard, which makes it so much nicer as a teacher. I just got to say, like, when you're a teacher, like, that's when it's great, is when students are working hard and trying to learn. It really makes it an enjoyable experience. So thanks to all of you for that. So that's the last of the material. I will stick around as always in Zoom, and then on Thursday I will try to get on early just in case anyone has, not that I'm going to be able to like help you with math, because it's probably going to be too late at that point to really help you with the math, but I'll be on there early just in case there's anything weird with the test not coming through right or any kind of weird behavior. I'll try to get on a little bit early, so if there's any kind of weird behavior, we can fix that before the actual final exam time. I will remind you, there is tutoring on campus. So if you need tutoring with any of this, make use of the tutoring center. There's paid tutors sitting in there, and my understanding is over the summer they're doing almost nothing. But there's paid tutors in there to help you. And then there is the Discord where you can all get together in a voice chat and go over the practice test together, or whatever it is that you want to do to get ready for that, and kind of get prepared for that. So is there any other questions or anything? No? Okay, well then I will see you on Thursday, and I think we're all set up for everything. So I'll stick around in Zoom for a few minutes till things kind of clear out. I'm going to shut down the YouTube stream. If anyone wants to hop into Zoom and talk to me, feel free to do so, please. Thanks, everyone.